Hello, my name is Kabila Haile Soboka. My project is called RibAssist 3D. The main question behind this project is simple. Can we find the 3D location of a rib fracture by using two CT-derived views, one from the front and one from the side, instead of analyzing the entire CT volume by using a full 3D model? RibAssist 3D takes an AP view and a lateral view and highlights possible fractures, predicts the rib level, and creates a 3D point only when it's confident that the finding in both views represents the same fracture. This is a proof of concept research. It's not a medical device or a diagnostic product at this stage. Rib fractures are important because both the number of fractures and their locations can affect trauma care, pain management, and injury severity assessment. However, finding every fracture in a CT scan and assigning the correct number can be slow and difficult for clinicians. My project follows three main principles. First, the system detects possible fractures and predicts their anatomical location. Second, it creates a 3D point only when there is a matching between the front and the side views is strong enough. And third and lastly, when the system is uncertain, it does not guess. It keeps the finding visible for review, and it does not create unreliable 3D locations. The main rule is simple: abstain instead of hallucinating. For the data, I use two public datasets. The first is RibFrac, which provides CT scans and rib fracture annotations, and the second one is RibSeg, which provides rib levels, center lines, and 3D rib anatomy. For each CT volume, I created two orthographic projections, an AP view from the front view and a lateral view from the side. These are simulated projections generated from CT scans. They are not independently acquired clinical X-rays. The data was divided by care, in which there were 325 cases for training, 65 cases for development and diagnosis experiments, and 55 cases in the final sealed test set. The sealed test set contained 601 fractures and was opened only once after the model thresholds and evaluation policies had already been fixed. Okay, let's dig deeper. First, two separate unit models analyze an AP and lateral projections. Each model creates a heat map showing possible fracture locations, and the heat maps are converted into candidate points. The system then compares the candidates from two views by using their shared vertical position. A one-to-one matching step tries to determine which AP point and lateral point represent the same fracture, and this matching step includes an absentation process. This means if the confidence is too low, the system does not create a 3D point. When a pair is accepted, the 2 points are back-propagated or back-projected and triangulated into a 3D location, and a separate addressing model predicts the side of the body and the rib number. For evaluations, a 3D point is considered correct when it's within 10 millimeters of the true fracture location. The project uses three learned components. The first component is the fracture detector. It uses two unit models, one for the AP view and one for the lateral view. The second component is the addressing model, and it uses information from both views to predict the side and the rib level. The third component is an experimental pair scoring model, and its purpose is to test whether the local image appearance could improve cross-view matching. The models are intentionally compact. The goal was to study the matching problem while keeping the system efficient enough for future deployments in low-resource healthcare settings like rural Ethiopia. This was the key experiment in the project. And instead of reporting only one final score, I evaluated each stage of the pipeline separately to identify the bottleneck. First, I verified the geometry, and the round-trip error was essentially zero. Then I supplied the correct cross-view correspondence, and the median error was about 4 millimeters, showing that the geometry and the localization were already working really well. The real problem appeared during the cross-view correspondence. The lateral detector produced many weak candidates, making the correct matching difficult. I tested better correspondence models, but they didn't improve the results, and retraining the lateral actually did. So the main bottleneck was the lateral detector's quality, not the geometry or the matching algorithm. Alright, let's talk about the results. The final result is best understood as the funnel rather than a single percentage. One sealed test set is about 61% of fractures were detected in both views for about 58%, and the correct match already existed in somewhere in the candidate graph. So the information we needed for the reconstruction was often available. The challenge was deciding which candidate pair to trust. Under the frozen confidence, the policy only got 15 out of 601 fractures and became correct 3D commitments, giving us around 2.5% end-to-end commitment yield. When the system did commit, it was actually accurate. The median localization error was about 1.49 millimeters, to which 93% were placed on the correct rib, and the system averaged around 0.43 false 3D points per case. The main takeaway is that the information is there, but the system still struggles to confidently convert available candidates into correct 3D constructions. Now I'd like to show you RibAssist in action by using one patient case. I'll start the pipeline, and just in a couple of seconds, the system finishes processing the case. The first thing we see is the case overview. From here, we can get a quick picture of everything the system found before looking at individual fractures. One feature I find especially useful is the 3D interactive model, that we can rotate it, zoom in, zoom out, and view the rib cages from different angles. And this makes it much more easier to understand where the injuries are in relation to one another. If I want to inspect a specific rib, I can simply select it from the rib navigator, and RibAssist highlights that rib and shows the related information automatically. Now let's review one of the findings, and I'll also turn on full case context so we can see this fracture in detail. Notice how the highlighted rib in the AP image matches the highlighted rib in the 3D model. That connection helps the reviewer move naturally between the image anatomy. Now let's look at another finding. Here the AP view and the lateral view and the 3D reconstruction all support the same result. And if we turn on the 3D map, we can actually see which parts of the image influence the detector the most. And based on that evidence, I'll accept this finding. Here is another example with a successful reconstruction. Again, both projections agree with the final 3D result. And I can also inspect the candidate peaks, and those are the possible fracture locations the system considered before deciding on the final match. Once the review is complete, the case summary brings everything together in one place. If I ever want to revisit a decision, I can reopen any finding with just a single click. This is how RibAssist supports the review process. Instead of asking the clinician to switch between different images and findings, it brings everything together into one organized workflow and helping them understand the complex rib fracture cases more efficiently while keeping the final destination in their hands. RibAssist 3D is designed to support the clinicians, not replace them. After a normal CT review, RibAssist actually highlights the suspicious fracture regions, predicts the rib number, and adds 3D location when the confidence is high. It also organizes multiple fractures into structured summary and preserves uncertain findings instead of hiding them. The clinician then reviews the evidence and decides whether to confirm, reject, or investigate the findings further. This project shows how fracture detection, anatomical addressing, and selective 3D localization can be combined into human-in-the-loop review workflow. Like any research project, RibAssist 3D have some important limitations. It's a research proof of concept, not a medical device or a clinical diagnostic tool. The inputs are CT-derived projections rather than real clinical X-rays, and the final test set is relatively small, and I have not conducted a clinical reader study yet. So while the project shows the selective 3D localization can be accurate, it's still an early stage system. Future work will focus more on improving coverage and validating the system in a realistic clinical setting. If I were starting this project again, I would invest in the lateral detector much earlier. The staged analysis showed that improving the detector quality had much bigger impact than improving the matching algorithm. From there, I would focus on a stronger anatomical correspondence, large and more realistic evaluations, and a clinician reader study. The main takeaway is that RibAssist 3D is more than a reconstruction system. It demonstrates an assistive workflow, it shows how staged evaluation can identify true bottlenecks, and it provides a clear direction for future improvements. My long-term goal is to keep building AI that is not only accurate but also efficient enough to be deployed in a resource-constrained healthcare settings like rural Ethiopia. Thank you, and I'm happy to take any questions through my email that is written on the slide. Thank you.